If you want to know how polluted a river is, you really shouldn't just look at the water.
Right, the surface is pretty misleading.
Exactly. The real danger, like the decades of invisible toxic waste that's threatening our local water supply, it isn't floating on the surface at all. It's hiding in the mud.
Yeah, lying right under the radar.
So for those of you listening whose livelihoods depend on water, whether you're managing local irrigation, running a utility plant, or, farming along a riverbank, you might think a clear-looking stream means you're totally safe.
But the sediment lying quietly at the bottom is actually this highly active, incredibly volatile vault.
Which is exactly why we're here. Welcome to today's deep dive. Our mission today is to really dissect the hidden chemical architecture of river mud.
Yeah, we're going to understand exactly how it traps municipal pollution.
And more importantly, how it can just suddenly trigger a massive release of that pollution right back into the water you rely on.
It's a phenomenal hidden mechanism, honestly.
Right.
And to unpack it, we are looking at a really specific environmental study focused on the Danshui River Estuary in northern Taiwan.
Okay, so northern Taiwan.
Right. And this paper gives us this microscopic layered look at the sediment profile. We are basically pulling back the water to look at the dirt beneath.
Just staring straight at the mud.
Exactly. It reveals this complex chemical drama that, frankly, plays out in waterways all around the world.
I mean, I have to admit, I struggle to see why the mud even matters at first glance. We're talking about a flowing river here, right?
Right, it's constantly moving.
So I look at the Taipei Metropolitan Basin. You have three major tributaries, the Keelung, the Dahan, and the Sediment rivers all converging.
That's a massive, massive hydrological system.
And you have over 7 million people living in this basin. That is a truly massive volume of domestic wastewater entering the system every day.
Oh, absolutely.
So even if that wastewater is heavily polluted today, shouldn't the sheer volume of water moving through the basin just, flush it all out to the ocean over time?
I mean, that's the logical assumption, right?
Yeah, why are we staring at the dirt?
The intuition makes sense. You see a river moving, you assume everything in it is moving toward the sea.
Yeah.
But pollution does not just wash away in a neat, linear fashion.
It doesn't.
No, a really significant percentage of it actually sinks. When we look at the wastewater entering the Danshui River Estuary, it is just heavily loaded with nutrients.
Like nitrogen and phosphorus.
Exactly. The dissolved nitrogen, specifically ammonium, frequently exceeds 500 micromoles.
Okay, wait, 500 micromoles, is that a lot?
It is staggering. To put that number in perspective, a healthy, balanced river environment might see a tiny, tiny fraction of that amount.
Wow. Okay.
This water is essentially operating as liquid fertilizer.
Yeah.
And the dissolved phosphorus, which is really the main culprit we were tracking today, exceeds 10 micromoles.
So we basically have an environment that's just overloaded with nitrogen and phosphorus.
Right.
And that means the water becomes highly eutrophic, creating those massive algal blooms that, turn the water thick and bright green.
Yeah, it looks like pea soup.
Right. I understand that the algae thrives on this liquid fertilizer, but again, doesn't that algae just float downstream?
Well, some of it does, sure. But you have to look at the physical properties of the phosphorus itself.
Okay, what do you mean?
So dissolved phosphorus has this incredibly high affinity for attaching itself to suspended particulate matter in the water.
Oh, so it grabs onto things.
Exactly. Every little fleck of silt, clay, or organic matter drifting in the river acts like a tiny raft. The phosphorus just binds to these particles.
So they're just hitching a ride.
Right. But as the river's flow slows down, which naturally happens when it widens out into an estuary, those tiny rafts lose their momentum.
Oh, I see. Gravity takes over.
Exactly. They drift down through the water column and settle right on the bottom. The pollution literally buries itself, building up layer by layer, year after year.
Okay, so the riverbed isn't just a physical container holding the water. It's actually a sponge soaking up all the city's waste.
That is a perfect way to look at it.
But to actually prove that, the researchers couldn't just test the surface water, right? They had to go down and get the mud.
They did. In May of 2021, the research team went out on a small fishing vessel to actually map this hidden landscape.
Out on a little fishing boat, just doing science.
Yeah, exactly. They established testing sites across 3 different zones. You have the upper estuary, which is closest to the urban center.
Okay.
Then the middle estuary, and finally the lower estuary where the river meets the ocean. Divers actually went down and drove these specialized tubes straight into the riverbed.
Like plunging a giant straw into the dirt.
Literally. They extracted these sediment cores that were up to 36 centimeters deep.
Oh, wow. So I'm picturing like a transparent cylinder of dense, heavy river sludge over a foot long.
That's exactly what it looks like.
You are basically looking at a vertical timeline of a river's history then, because the deeper you go, the older the mud, right?
Exactly. It's a cross-section of time.
So what did that timeline actually reveal about the phosphorus?
It revealed this staggering pollution footprint. By slicing up those cores and analyzing the total phosphorus trapped in the mud, they found a very sharp gradient.
A gradient, meaning it changed depending on where they were.
Right. Up in the upper estuary, right where the urban wastewater impact is the heaviest, the mud is highly polluted.
How high is highly polluted?
The total phosphorus averaged over 2,160 milligrams per kilogram of sediment.
Oh, wow.
Yeah. And in certain hotspots, it actually peaked well over 2,450 milligrams per kilogram.
That sounds incredibly dense. And then what happens as you track the river's path down toward the ocean?
The concentration just falls dramatically. In the middle estuary, that average drops to about 1,360 milligrams per kilogram.
Okay, so it's nearly cut in half.
Yeah, and by the time you reach the lower estuary, it falls to 685 milligrams per kilogram.
So the sediment closest to the city is just holding this massive, dense stockpile of phosphorus.
A huge stockpile.
I mean, that pollution footprint makes total logical sense. The city dumps the waste, the heaviest particles drop out first right by the city, and the rest sort of slowly fades out as the river pushes toward the coast.
Right, the physics of it are pretty straightforward.
But knowing how much phosphorus is down there doesn't really tell us what it is actually doing.
No, it doesn't.
Because if it's just buried in the mud, maybe it's inert. Maybe the riverbed is actually safely storing it away from us.
And that is the pivotal question of the whole study. Phosphorus in sediment isn't just one monolithic, uniform substance.
It's not.
No. It exists in multiple distinct chemical forms. And those specific forms dictate whether the phosphorus stays safely buried or becomes a major threat.
Okay, so to figure out the exact nature of this stockpile, what did they do?
The researchers applied a really complex chemical process called the sequential extraction method.
Sequential extraction? Okay, so how does that work? Are they just like putting the mud under a microscope and looking at it?
It is far more aggressive than that. Think of it like a series of chemical sieves.
Okay, sieves.
You take a sample of that sediment core and you wash it with a specific, really mild solvent. That solvent strips away only the most loosely attached phosphorus.
And then they measure that.
Right. Then you take the remaining mud and you wash it with a slightly harsher solvent. This one targets phosphorus that's bound to different, tougher minerals.
Oh, I get it. So you just repeat this process step by step using increasingly aggressive chemicals.
Exactly. Until you have separated all the phosphorus into 5 distinct fractions based on exactly what it was clinging to.
So you are systematically dismantling the mud to see how the building blocks are actually connected.
Piece by piece.
When they ran the sequential extraction on those highly polluted upper estuary cores, what did they find at the bottom of the sieves?
The data revealed something pretty incredible. In that highly polluted upper estuary zone, a massive 80% of all the phosphorus in the sediment was bound to one specific element.
Wait, 80%? Just to one element?
Yes, iron.
Iron.
Specifically, it was ferric iron-bound phosphorus. The phosphorus wasn't just resting in the dirt, freely. It was chemically locked to iron molecules.
80% is an overwhelming majority. But where is all this iron even coming from?
That is the really fascinating part.
Because a city's wastewater stream is full of, human waste, soaps, maybe some agricultural runoff. Why is there a massive deposit of iron just waiting in the estuary?
The iron is actually there on purpose.
On purpose?
Yeah, it traces directly back to human engineering. Modern wastewater treatment plants frequently use iron salts as a coagulant.
Oh, really?
Yes. When they're treating municipal sludge, they add iron to help clump the waste together so it's easier to remove from the water.
Okay, that makes sense.
But crucially, they also use iron to bind with hydrogen sulfide.
Hydrogen sulfide. Wait, is that the stuff that smells awful?
Exactly. It's what causes that terrible rotten egg smell in sewage. So by adding iron, cities can suppress the odor and drastically improve the air quality right around the treatment plants.
Wait, let me make sure I'm grasping this because this is wild. The city intentionally uses iron to treat the wastewater and stop it from smelling terrible.
Right.
And then that treated water, which is now carrying all this dissolved iron, flows out into the Danshui River.
Yes.
And once it is in the river, that iron acts like a giant magnet. It just grabs onto the excess dissolved phosphorus floating in the water, binds to it, and drags it straight down into the sediment.
Exactly. The pollution treatment itself is creating the mechanism that buries the phosphorus in the mud.
It's like the city built its own trap by accident.
It is this fascinating, completely unintended consequence of urban water management. The iron successfully pulls the inorganic phosphorus out of the water column.
Which clears the surface water up.
Right, and it sequesters that huge nutrient load down into the mud.
I mean, I am looking at this from the perspective of a local water manager, and honestly, this sounds like a massive victory.
It does sound like a win initially.
Because if the iron is acting like a set of, let's say, chemical handcuffs arresting the phosphorus, pulling it out of the flowing water and burying it deep in the riverbed, doesn't that mean the water flowing past our farms and cities is clean? The handcuffs are keeping the pollution locked away in the vault? Why is this a problem?
Because on the surface, it looks like a perfect natural filtration system. You have successfully swept the dirt under the rug, so to speak.
Right.
But the vulnerability lies in the actual nature of those chemical handcuffs. They are not permanent.
Oh.
The bond between iron and phosphorus is highly sensitive to the surrounding environment. Specifically, it depends entirely on the presence of oxygen.
Oxygen in the water.
Yes. Iron only maintains its tight grip on phosphorus when there is ample dissolved oxygen in the water. It requires what we call an oxic environment.
Okay, so as long as the river has enough oxygen, the handcuffs stay locked. The phosphorus stays put.
Exactly. But earlier you mentioned this specific river is overflowing with nutrients and choking on thick green algal bloom.
Yeah, all that liquid fertilizer we talked about.
And that is the catalyst for the disaster here. The excess nutrients cause the algae to reproduce explosively. The surface of the river basically becomes a thick mat of green.
Which blocks out the sun, right?
Right. But more importantly, algae has a really short lifespan. When that massive volume of algae dies, it sinks straight to the bottom.
Where all the mud is.
Exactly. And bacteria immediately begin decomposing all that dead plant matter. That decomposition process aggressively consumes the dissolved oxygen in the water.
Oh, I see where this is going. The river becomes so highly eutrophic that the decay process just chokes the oxygen completely out of the water column.
It does. It drives the bottom layers into hypoxia. The water right at the sediment boundary goes hypoxic, or sometimes even completely anoxic.
Anoxic meaning zero oxygen.
The oxygen is just gone. And without oxygen, the chemical environment of the mud shifts entirely. The iron undergoes this process called reductive dissolution.
Reductive dissolution. Does that mean the iron dissolves?
It dissolves. The chemical handcuffs break wide open.
Oh, wow.
And when that happens, all of that trapped phosphorus, that massive 80% stockpile representing literal decades of buried urban wastewater, just floods right back out of the sediment and into the overlying water.
That is insane. So if iron binds phosphorus, but only in oxygen-rich environments, and this river is choking on algae that actively depletes the oxygen,
Yep.
you are telling me the pollution itself is what ultimately breaks the handcuffs. The nutrients feed the algae kills the oxygen, the lack of oxygen breaks the iron bond, and suddenly the mud violently exhales years of stored phosphorus back into the water.
It is a totally devastating feedback loop. The release of that legacy phosphorus provides an immediate, massive dose of fresh fertilizer to the water.
Which fuels an even larger algal bloom.
Exactly. Which then subsequently dies, sinks, and consumes even more oxygen, keeping the handcuffs broken.
See, this is why this matters so intensely to you listening. Let's say you manage a local utility, right? And you pass strict regulations tomorrow. You completely stop all new phosphorus from entering your river.
Which is a huge undertaking on its own.
Right. You upgrade the treatment plants, you stop all the agricultural runoff, you pat yourself on the back and think your river is saved.
But it isn't.
But your river isn't fixed. The mud at the bottom is holding this massive invisible stockpile of legacy pollution. The moment the water gets warm on a hot summer day and the oxygen levels naturally drop, the mud just releases a toxic payload right into your intake pipes.
It really is a ticking time bomb. That is the harsh reality of legacy pollution. You cannot just manage the inflow.
You have to look at what's already there.
Yes. You have to account for the internal loading. That's what we call the pollution. The river is feeding itself from its own bed. And honestly, the chemistry of this internal loading is actually even more complex.
Wait, more complex?
Yeah. Iron is the primary mechanism, obviously, but the researchers found it does not act alone down there.
Okay, what else is down there manipulating this cycle?
Manganese.
Manganese. Okay.
When the team analyzed the sediment cores, they found that manganese behaves very similarly to iron, but with some pretty crucial differences.
Such as?
Well, in the highly polluted upper and middle estuary, the profile of where manganese is concentrated in the mud strongly correlates with the phosphorus footprint.
So they hang out together.
Basically, yes. And more importantly, over 80% of the manganese they found down there was in a non-residual form.
Non-residual, meaning it's highly reactive, doesn't just sit there like a rock.
Exactly. It is incredibly sensitive to the environment. Manganese is also a redox-sensitive element, which means it reacts to dropping oxygen levels, just like iron.
But you said there was a crucial difference.
Right. Manganese actually requires a higher threshold of oxygen to stay stable than iron does.
Wait, really? So if the oxygen starts to slowly drop, the manganese is going to break down before the iron does?
Yes, that's exactly it. Manganese acts almost like an early warning system, or really a first trigger.
Oh, that's wild.
As the oxygen levels begin to decline from the decaying algae, the manganese-bound phosphorus dissolves first. This releases an initial wave of nutrients into the water.
Which accelerates the algal growth even more.
Exactly. It accelerates the growth and the subsequent oxygen depletion, pushing the environment further and further into hypoxia until the massive iron vault finally breaches.
It is literally a cascading chemical failure.
That's a perfect description.
It is terrifying to think of the riverbed operating with these layered, sequential chemical triggers.
It really is.
But, the paper also noted a significant change as you move down the estuary. The iron handcuffs are super dominant near the city. What happens as the river finally widens out and meets the salty water of the ocean?
The entire chemical profile shifts.
Yeah.
In the lower estuary sediment cores, the percentage of phosphorus bound to iron drops significantly.
How far does it drop?
It falls to around 50%. And meanwhile, a completely different fraction of phosphorus rises to take its place.
Okay, what replaces it?
The sequential extraction method revealed that in the lower estuary, up to 30% of the phosphorus is what they call detrital phosphorus.
Detrital. Let's break that down for the listener. What exactly makes phosphorus detrital?
Detrital phosphorus is essentially natural geologic phosphorus. It is firmly locked away inside the crystalline structures of tiny rock fragments and minerals.
So it didn't come from human wastewater or agricultural runoff?
Nope. It was just weathered off the mountains and washed down the river completely naturally.
So it's essentially just microscopic gravel.
That's a really good way to look at it. And the crucial difference here is stability.
Because it's locked in a rock.
Right. Unlike iron or manganese, detrital phosphorus does not care at all about the oxygen levels in the water. It is a non-labile fraction, meaning it does not readily dissolve or react to hypoxia.
It just sits there.
It just safely sits there, securely locked inside its rocky casing, eventually becoming part of the ocean floor.
So the further away from the urban center you get, the more the mud basically returns to a stable, natural geologic state. The human-made chemical traps sort of fade out.
They fade, yes.
Yeah.
But they do not disappear entirely. 50% iron-bound phosphorus in the lower estuary is still a really significant load of potential pollution.
Just waiting for the right conditions to release.
Exactly.
And speaking of those conditions, I really want to pivot to a glaring environmental factor here. We've spent this whole deep dive talking about a delicate, microscopic chemical balance.
We have.
We were talking about slow, seasonal algae blooms and gradual oxygen depletion. But Taiwan is famous for its extreme weather.
Oh, absolutely.
The paper specifically brings up the impact of typhoons. My immediate thought is, if a typhoon brings torrential rain and massive winds, it must aggressively churn the water.
It churns it up wildly.
So wouldn't that churning force massive amounts of oxygen down to the riverbed? Wouldn't a typhoon actually fix the hypoxia, lock the chemical handcuffs back up, and secure the phosphorus?
You would think all that turbulent mixing would be a great thing for the oxygen levels.
Right.
But a typhoon introduces a completely different, incredibly destructive physical force. The paper points out that during summer typhoons in the Pacific Northwest, Taiwan can receive over 1,000 millimeters of rainfall in a remarkably short period.
Wait, 1,000 millimeters? That is literally a meter of water dropping onto the steep terrain of the Taipei Basin.
A meter of water.
The velocity of the runoff entering the river must be just apocalyptic.
It creates what geologists call a hyperpycnal flow. The sheer volume and speed of the water tearing down the mountainsides and through the city pick up immense amounts of dirt and debris.
It's basically a mudslide.
Pretty much.
Mm-hmm.
The river water becomes so dense with suspended mud exceeding 40 grams of particulate matter per liter that it physically changes how the river flows.
Because the water is just so heavy.
The water becomes incredibly heavy. It sinks. And it physically scours the bottom of the estuary.
So it acts like a liquid avalanche tearing through the riverbed.
Exactly. And remember those carefully layered sediment cores we talked about earlier?
Yeah, the vertical timelines of pollution.
Right. Well, a hyperpycnal event violently rips those layers apart. It completely scours the riverbed, breaking up the mud and lifting all those decades of buried iron-bound phosphorus right back into the water column.
Oh, wow. It completely erases the careful chemical stratification we just mapped out.
It completely erases it.
The physical violence of the water just absolutely overpowers the chemistry.
It mobilizes the entire stockpile all at once. And while the immediate river might technically be highly oxygenated from the storm, all that unearthed iron-bound phosphorus is now being aggressively flushed out.
Flushed right into the coastal ocean or pushed into downstream agricultural intakes.
Exactly. When the storm passes, the water calms down, the mud settles in brand new locations, and the delicate, dangerous cycle of hypoxia and release just begins all over again.
It paints a picture of an underwater ecosystem that is entirely dynamic. We think of mud as just, inert dirt, but it is this living, breathing chemical engine.
It never stops moving.
So what is the ultimate takeaway for you listening right now? We started this deep dive looking at the murky surface of the river, assuming that the visible water was the whole story.
But it's only half the story.
But the real lesson is that the riverbed is holding the memory of our pollution. The mud acts as a vault, using iron from our own treatment plants to lock away phosphorus when the water is healthy and oxygenated.
Which is a great temporary fix.
But the moment we let the nutrients get out of hand, the moment the algae blooms and the oxygen drops, those vault doors just swing wide open. The mud releases years of stored toxicity back into the water we need to irrigate our crops and run our cities.
Understanding this hidden cycle really is the absolute baseline for protecting any local water system.
You just can't ignore the mud.
You cannot just treat the water flowing out of the pipe today. You must account for the chemical stockpiles already waiting in the sediment below, because the sediment is dictating the health of the water from the bottom up.
You definitely have to respect the mud. And that brings us to a final thought I want to leave you with today.
Okay, let's hear it.
The paper we explored focused exclusively on the mechanics of the Danshui River estuary in Taiwan.
Right.
But the chemistry of iron, phosphorus, and oxygen is universal.
Completely universal.
If global climate change is causing our rivers, our lakes, and our coastal waters to gradually warm up, and physics dictates that warmer water naturally holds significantly less dissolved oxygen than cold water.
Oh, I see where you're going with this.
Are we on the verge of accidentally unlocking decades of buried iron-bound phosphorus in riverbeds all over the globe, all at exactly the same time?
That is a terrifying thought.
It is a hidden threshold we might be crossing without ever looking below the surface. Just something to ponder the next time you look out over a quiet river. Thanks for joining us on this deep dive.